Hello, everyone. Welcome. A little intro to this workshop. This is going to be our first workshop for the Algorand Hackathon. It's going to be on building on smart contracts with Algorand. We have a great team today that are going to speak for you guys. A little update on the hackathon. We are still accepting registrations. So if you still want to register your team for the hackathon, please do so. I'm going to paste the link here in the chat, but we'll get right into it. We have Jason from Algorand Foundation with us. He's the senior dev of dev relations on with us today. He's going to speak for us. But yeah, we'll get right into it. Jason, do you want to take over here?
Hi, my name is Jason Weathersby. I run developer relations at Algorand, and I'm going to be covering Algorand Smart Contracts today. As an way of overview of the topics and agendas that I'm going to go through, I'm going to first give you a brief overview of how smart contracts are, how they function, how they're architected, and then we'll talk a little bit about how the language you write smart contracts in. That's the TEAL language, and then finally, we'll discuss developing smart contracts using Python. And I'm going to show you a couple examples in each one of these and also show you a little bit about debugging so you can get an idea of how to do that. And then also, I'll cover right at the end briefly how to call smart contracts from the Python SDK once they're deployed. So, but before doing that, I wanted to walk through what Algorand, a typical Dapp architecture looks like on the Algorand blockchain. So typically we have our Algorand blockchain sitting out in the sitting out there, and on the blockchain we have algos. That's our primary token that we use, the primary token we use for the network, and and then we also have something called ASAs. Now, what ASAs are just basically a simple element on Algorand that represent tokenization of any asset. That can be NFTs, FTs, security tokens. They're highly configurable, but they don't require that you use a smart contract to build them. If you're used to other blockchains, that'll be a difference for you. But so you essentially can create your own token, right? And then we also have smart contracts. Smart contracts that are out there, these are pieces of logic that live on the blockchain, and this is what the primary discussion will be about in this topic today. But if you have an app somewhere off chain that you want to use the blockchain, the main way you communicate to our blockchain is through transactions. And to do that, we use one of Algorand's SDKs, and we have the official ones are Go, JavaScript, Java, and Python. And there's a bunch of community supported ones. There's C# out there, a bunch of different SDKs available to use with Algorand. It's a REST endpoint, so it's fairly easy to implement additional languages. All right, so everything, but the thing about transactions, they all have to be signed. And typically, this is where you're going to make your first choice if you're constructing a DApp is, do you want to do key management? If you do, then most likely you'll do all the signing inside of your app and you manage the keys. If you don't want to do that, you need some type of wallet so the individual user coming to the DApp will be able to sign those particular transactions. If you're using that approach, you got a couple different approaches you can take. First thing you can do is use the Wallet Connect JavaScript library in your app, and that allows you to present barcodes for people to sign transactions with the Para mobile wallet, which is the primary mobile Algorand wallet out there. Then you can also use the Algo Signer SDK. This is basically a Chrome plugin, functions a lot like MetaMask, if you're familiar with that, and it allows you users to sign transactions and manages the keys inside that plugin. You can also use the MyAlgo JavaScript library, which allows you to do basically the same thing the Chrome plugin does, except it's all in a self-contained JavaScript library. There's some additional, there's other wallets in Algorand. These are the primary ones that are being used right now, but there are definitely others. Take a look at our community page on the developer site, and you'll get an idea of the different wallets that are available. So this is a typical Dapp architecture. Today's talk was just going to be about smart contracts. And I will say we do have the language we use to write smart contracts is actually applicable to either smart contracts or smart signatures. Smart signatures are a little bit different than smart contracts. Are actually evaluated when you submit a transaction and don't live on the network. Smart contracts live on the network. That's the primary difference between the two. All right, and so we're going to primarily focus just on smart contracts. So what is a smart contract? I got to try to move this bar out of the way somehow. Okay, a smart contract is just a piece of logic that lives on the network. All right, and it's initiated by a transaction. You deploy it with a transaction, and once you deploy it, it runs the code the first time you deploy it. And then every time you want that code to execute again, you send a transaction to the network, and it'll run that piece of code. Its primary job is just to return true or false. That's its job. It's going to either approve or deny that transaction. And then one other thing to note is that particular transaction that initiates your smart contract can also be grouped with other transactions. Like I may want to do a payment transaction and call a smart contract. If the smart contract fails, I want the payment transaction to fail. Well, because they're atomically grouped, if any one of them fails, they all fail. They all must succeed to be successful. So, and these contracts are written in a language called TEAL, which stands for Transaction Execution and Approval Language. They can also be written in Python using our PyTeal library, or you can use them. They can be automatically generated using the Reach framework. And I believe up next week you're going to be getting a talk on the Reach framework and how it works with Algorand. But essentially, that's all a smart contract is. Now, how it actually executes, hang on a second. Okay, how it executes is once it's deployed, if you issue an application transaction, you got logic in the smart contract. Well, it reads data up from the ledger, reads information on the transaction, and this may be one or more transactions. So if you've got the main primary application transaction, and then you've got a payment transaction, the contract logic can actually read them both. All right, so that determines whether it passes or fails. The contract can store some global values for the particular contract. It can also store some local values for any user that is opted into the smart contract. Additionally, a smart contract can also issue other Algorand transactions. These include payment transactions, asset transactions, and in fact, even other smart contract application transactions. Anytime you call a smart contract, we refer to that as an application transaction, and we'll discuss more of that in just a minute. But from digging down a little bit lower level, smart contracts actually written in two programs. We call that the approval program and the clear program. And which program runs depends on the type of application transaction you issue. Now, one other thing I'll say about global and local state, right now, global state allows you to write in key value pairs, up to 64 key value pairs of up to 128 bytes of data each. So that's fairly limited size in global state. And but that's for the contract itself. And then for every user that opts into the smart contract, they can store up to 16 KV pairs. And these are all that's stored per user. So you might think of, if I'm doing a crowdfunding app and I donate money, I might want to store how much that particular individual stored in their local state, not in global state. And it's fairly limited. I will tell you by the end of the summer, we're expecting one more atomic that's going to go inside of global that allows you to basically have unlimited global state. And we're calling these boxes currently, but you'll be able to on the blockchain, you'll be able to store these large size blocks that you can put any data in that you want. But right now, this is the way the system is today. And so now, like I said, which program runs depends on the type of application transaction you issue. We have 6 application transaction types, and these are laid out here. And depending on which one of these you issue will determine which program you run. We think of the approval program. When you think of that, just think that's my normal logic. That's where I'm going to put the bulk of my application logic. The clear program is really used to clean up an application when someone opts out of your application. So the first subtype of application transaction is called a no-op. And a no-op is just a generic call. This is the call that you'll use when you deploy the contract or anytime you just want to call a native method on the particular contract. Then we have opt-in. This is used if you want to store local state values per user, they have to opt in. And so this is so you can't spam their account with all kind of extra data. And so that's what the opt-in transaction. Smart contracts on Algorand can also be deleted and updated unless you specifically put in the logic to reject those transaction types. And then we have a closeout transaction. Anytime you opt in, you got to be able to opt out. That's what the closeout transaction type does. The only problem with that particular piece of logic is if the TEAL logic fails, then I'm stuck in a smart contract. So how do I get out of it? All right. Well, then that's where the clear transaction type comes from. It'll initiate the clear program, and whether the logic passes or fails, the user will be removed from the smart contract. And the reason I bring these up is because the first thing you're going to build in most contracts is how do you have to route your logic based on which one of these subtypes of application transactions is being called. All right. So we call closeout graceful, and the non-graceful way is to use the clear. Smart contracts can also be used as escrows, and this is one of the primary things that you can do with smart contracts now. So let's say I deploy my smart contract to the Algorand blockchain. Well, what it's going to do is, as soon as you run it, it's going to return, deploy it, it's going to return an Algorand address and a unique ID. This unique ID is called its application ID. When your logic and your code runs for the very first time, its value will be set to 0. So you can actually check to see if you're being deployed just by looking for an application ID of 0. At the end of its deployment, it'll return a unique ID for that particular smart contract. You will use this ID to call that smart contract with application transactions later on. And then, but the unique thing about having the Algorand address is just like any other address on Algorand. You can now send algos or ASAs into the smart contract from any other account on the Algorand network. And then it essentially locks them into that escrow until the logic allows them to leave the escrow. And the way this is done is using something called inner transactions. Every time your smart contract runs, it can run up to 256 inner transactions. And what these are, I want to issue a payment transaction. I want to transfer an ASA or transfer some algos. I want to freeze an asset or claw back an asset. In fact, you could even create a whole new asset class in a smart contract. And obviously, smart contracts can be short-lived, long-lived. You can actually, create another smart contract or delete another smart contract through a smart inner transaction. But the primary thing you'll see is one smart contract call another smart contract. That's called an application inner transaction. In fact, you can actually nest up to 8 levels deep of inner transactions of nested smart contract calls. So that gives quite a bit of power in smart contracts and their ability to communicate across. From a runtime architecture on the Algorand AVM, it kind of looks like this. Here's my, think of my AVM runtime on the right side. That's going to be, the AVM is going to run on every Algorand node. I issue an application transaction. I'm going to pass some data with that particular call. One of them is called the accounts array. And this is basically an array of accounts that you want to have larger access to in the ledger, meaning you want to read more of their data. And then we have an applications array. If I want to call another smart contract, I'm going to need to have that in that applications array. And then an assets array, if I want to interrogate a specific ASA that's on the Algorand blockchain, I can look at the assets. I have to pass that asset in the assets array to the application transaction. And those 3 arrays right there, they can change per application transaction. So you can change up that list. And then finally, we have the arguments array. Now, this is you can have up to 16 arguments, 2 kilobytes of data in the arguments array. It's just for standard arguments that you want to pass to the application, to the smart contract. What these do is these restrict how much of the ledger the smart contract's allowed to read. And the reason we do it this way is Algorand has extremely high performance and getting ready to get a massive boost in performance. And the way we do this is by doing restricting the view of the entire ledger per run of the smart contract. So you have to be very focused about what you're trying to achieve in those smart contracts. Well, what the AVM does is it loads your TEAL program up. It has a stack engine that's sitting in it, and it processes your program one line at a time. And what inside your TEAL program, your smart contract, you have access to a set of global variables that are available. These may be things like what's the latest timestamp. And then you also have the transaction properties. This may be the current application transaction or any other transaction that happens to be grouped with this. And if you've already gone through the initial training on Algorand, you'll know that an atomic transaction group can hold up to 16 different transactions. All right, so those are read-only. Well, while you're in there, you can also read and write global and local state key value pairs. That's the global and local state that we talked about earlier. And then you have this little temporary scratch space that goes away after the run, but you can write things to the scratch space. And then finally, you can issue up to 256 inner transactions. And you can actually group those inner transactions as well if need be. So that's the high-level runtime architecture of the way a smart contract's processed and where it sits in the Algorand ecosystem. All right, so before getting into how you actually write these smart contracts, I want to take a quick glance at something we call the ABI. And the reason I'm going to do this is in the two examples that I'm going to show you today, both of them make use of the ABI. What the ABI is just it's a standard for describing methods, interfaces, and contracts. And these three artifacts are described in the JSON files. Well, the SDK is set up to read and convert these into proper smart contract calls with parameter types and return types that all handle for you. And so what a method is just a description of what the method name is, the type of arguments it takes, and then its return types. An interface is just a collection of these methods. And then a contract is similar to an interface and is just a collection of methods, but it has a concrete instance of a smart contract that's already live on the Algorand network. And so you can think of interfaces would primarily be used for creating standards and things like that. Contracts are, I want to show what methods my smart contract has to the world and describe that in a JSON file that I make publicly available. And this is called, we call this the ABI, which just stands for Application Binary Interface. It's a way to allow composability between apps and things like that in a structured way. So as an example of what a method looks like, we're going to implement this method later in Python, but this is an add method. And this method's description says I want to add X to a global integer. So, and X is going to be my first parameter. Its type is a uint64. And then it's the other things are the name of the parameter and description. And then the return type is going to return the current value of the global integer. That, when the SDK processes that JSON file, it actually produces something called a method signature, which takes the bare minimum data it needs to be able to send to the smart contract so the smart contract can switch off of that and know which piece of logic to actually execute. We call this a method signature. And you can see here, it says add, pass a uint64, get back a uint64. That's all this method signature does. And so this is all, the entire ABI specification is described in ARC4. There's the link for it. And by the way, Ryan or Russ should be posting a link to all the source code you're going to see in here, which also contains the presentation as well, so you can get the links out of this. The second one is just a document describing the ABI and some smart contract calls. Finally, I did a talk on the ABI at Decipher last year, and if you want to take a look at that, there's a YouTube video you can watch with an hour-long talk on the ABI. So this is all I'm going to say about the ABI, but I'll show you how you process ABI requests in the smart contract and how you handle return types in the smart contract as well. So how do I write smart contracts? Well, I'm going to start with the base level, how you write them in what we call TEAL, because I think it's great to have a great understanding of how it works on the core before we start wrapping it in Python. All right, so what is TEAL? TEAL is a bytecode-based stack language. All it does is it processes your program one line at a time, pushing and popping values off the stack engine that runs in the AVM. It's a Turing complete language. It supports looping and subroutines. And it, like I said, it processes your program one by one, pushing values and popping values off the stack. Now, the stack only supports two data types, and that's a uint64 positive value and byte arrays. Those are the only two things that the stack supports. At the end of running through your complete code, your contract's going to return true or false based on what's left on the stack. If you have a 0 at the top of the stack, it'll return a false. If you have a positive value at the top of the stack, and only one positive value, it'll return true. If you have multiple positive values on the stack, then you'll return false unless you use the return opcode, which basically says, just give me the last value and return that as my true false value. So that's the sole job of the smart contract stack engine, is just to process your program line by line and push and pop values off the stack based on something we call opcodes. Opcodes, think of opcodes as kind of like a function. They operate on your transaction data, your global data, and any parameters you provide, and they push and pop values off the stack. And we'll discuss a particular example of this in just a second. But there's over 148 opcodes in Algorand that are defined currently, and that list is growing. So as a simple example, let me walk through, I show this example a lot, it's pretty simple, but let's assume I have a 3-line smart contract program. And it seems pretty cryptic, it looks very similar-like, and it is, but it's really the way, because it processes one line at a time and it's just operating on a stacked engine, it turns out to be fairly simple. First line in this code, when this code is read by the AVM and processed, it's looking at that TXN opcode, which is an opcode. That opcode is followed by a specific property of the transaction you want to actually see. And in this case, it happens to be the transaction amount. So when the AVM processes that line, it pushes the transaction amount onto the top of the stack. Then the next line is int 1000. Now, all that's a pseudo opcode that just pushes an integer onto the stack, in this case, 1000. And we have those, you have one for bytes and ints. Those are the two things that you primarily, that's the only thing you can put on the stack. So there's some pseudo opcodes for each one of those. So here I'm just pushing 1000 on top of the stack. You'll notice the transaction amount gets pushed down. Then we get to the greater than or equal to. That's an opcode that pops those two values off the stack and pushes either a 0 or 1 onto the top of the stack, depending on if the first parameter is greater than or equal to the second parameter. And so the two parameters is, it obviously takes two parameters, and these are defined as, you can look at the pops section on the description below, is uint64A, uint64B. And you can see it said, this little brief description of a document here says it pops two values and it pushes one uint64, and then you get a description. Every opcode in Algorand in TEAL has a description just like this. Some opcodes don't push anything on the stack. Some don't pop anything from the stack. Every opcode has a definition that explains exactly what it does to the stack, because that's ultimately all that matters. What's left on the stack at the end of my run. So as an example, you saw me use the TXN opcode. Well, there's a whole table of properties that I can pull transaction stuff out. I'm only showing two of the fields right here, which are sender and fee. And those are just two fields that you'll notice that when I call that opcode, nothing pops off the stack, but it can push any. When it says any, it means it can push a uint64 or a byte array. And in this particular case, I'm showing one of each. The sender is a byte array and the fee is a uint64. And if you want to see all the documentation, here's a reference list, and you can see this is the list of opcodes that we currently support. And there's a bunch of them. All right, so let me go back. All right, so let me, I'm going to show a simple demo and walk through a simple TEAL example through the debugger, because that tends to be the best way to explain this. Let me just move that for a second. All right, so here's a simple TEAL program. By the way, that you should have access to the GitHub account. There's a couple main directories in here. This is the goal directory I'm looking in right now, and it's simple.tl. And the reason it's called goal is because I'm using the goal command line tool to deploy the smart contract and call it. I'll show you later how we do that with Python. But here is just the version of TEAL I'm currently using, processing. Right now, Algorand's at version 6, and next version will be version 7. Now, this particular TXN application ID is that application ID I talked to you about earlier. When this program first deploys, that value is going to be 0. Then we have this BZ opcode. What does that do? Well, BZ opcode is basically a branch opcode. And there's 3 branch opcodes. There's BZ, BNZ, and B. BZ happens to branch if there's a 0 on top of the stack. BNZ branches if there's a 1 on top of the stack. And B branches regardless of what's on the stack. And it branches to this label. And right here, I'm saying handle create app. Well, handle create app is right here at the bottom. And all it does is push a 1 on top of the stack and returns. So basically what it's saying is if someone deploys it, just approve the transaction. All right, so the next thing that we said, when I'm running it the second time, this will not be 0 anymore. So this won't happen, and then this line of code will be processed. This is that method signature I told you about. This is the TEAL method to do the comparison. When you're using the ABI, the method must be in the application arg 0. So you remember that application arguments array, and the first slot will always be the method signature. And so in this particular case, I'm loading the method signature for this method. This is what I'm expecting, and then I'm comparing that what's in the application arg 0. And then I'm using the equal, which puts a 1 or 0 on top of the stack, depending on if these two are equal or not. Now, if it has a 1 on top of the stack, this assert opcode automatically fails if there's a 0 on top of the stack. So this is kind of a way of just quickly doing an error check here. So what this says is if this smart contract is called at any time without calling the add method, it's just going to fail. And then the next thing I'm going to do is I'm going to get the second argument to the application, to the smart contract call, and it's and I'm gonna this particular method signature is called add, takes 2 uint64s and returns a uint64. So I'm just basically adding the 2 numbers together and returning the value. So I have application arg1 and 2 here. Those are the second and third arguments in that array. Now you'll notice this b to I thing. That's all that does is every parameter, regardless of type, is always passed as a byte array in Algorand. So the first thing I have to do is take this and convert it to an integer. That's what b to I does, byte to integer. And so this byte array gets converted to an integer, second argument gets converted to an integer, pushed on the stack, and I'm going to call the plus opcode, which adds those 2 together. This is how you store in scratch space. This is stored 0. So I'm putting it in the scratch space in the store in the 0th slot. Now this is where it gets a little strange. This is for handling the ABI return type. And the way we do this is, by the way, this is a pseudo opcode for loading a byte string on a byte array onto the stack. So this little byte array right here is all it is literally the word return hashed. All right. And so I'm hashing that, and this is what this is. All right, so that is what we use all throughout our smart contracts to determine if you're getting ready to signal the system that you're returning an ABI return type. So here I first load this on the stack, then I load the value that I had accumulated, which would be, if I pass 1 and 1, it'll be 2. And then I'm converting that back to a byte array, because anytime anything comes out of the system, it has to be converted back to a byte array. So, and then I'm concatenating this with that value. And so that's all that does is put those 2 together, and then I'm using this log opcode. Now what log does, it allows me to write up to a kilobyte of data into the completed transaction. And this is, you can call this thing up to 32 times and put any byte array data in it you want. If you want it to be used by the ABI framework, you have to put this little return string in it. So all this code is just to handle returning the right type. And then the last thing I'm going to do after I log that return value is load a 1 on the stack and return. So the way I would run this is, let me see, go, and I have this little create simple script, shell script here. I'm not going to get into it too much, but I have Sandbox running in the background. Sandbox is just a Docker instance of a development environment for developing smart contracts or any Algorand application. And it allows me to communicate with it, let it process my transaction calls. So I'm first connecting up to that, and here's where I'm actually creating the smart contract. And there's my approval program. I'm giving it the name of my approval program and the name of my clear program. And then these things right here are just, you have to, if you're going to use global and local state, you have to specify when you first create the contract, how much of the global state and local state are you going to use. So these parameters are used to set those. And then I'm going to echo that app ID that I'm getting back from deploying my smart contract there. So I'm not going to spend too much time on that. This is the important one I want to show you. This is how you call a method. You call goal app method, and then you call the specific ID that you're calling, that app ID you get back. And then this is how I call a method. I want to call add uint64, 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 my method. And then I'm gonna pass two arguments, arg1, arg2, and I'm just passing 1 and 1. And this is who the app call the transaction is coming from. Now, these are a little bit strange. This is so I can show you how to debug it. I'm writing, instead of writing out and sending it to my node, I'm actually writing out to a file and using this dry run dump indicator. So it creates this temporary how the node would have processed it had I submitted it. And it allows me to walk through the code line by line. And I'm doing that by using this TEAL, our TEAL debugger. That's what this is. And I'm using debug. This is the name of the TEAL file we looked at. And I'm using this dry run dump I created here, and I'm just setting a port to connect to it with the Chrome developer tools. So if I run this, okay, it's deploying my contract, and you'll see an ID show up. It's application ID 11, and now it's sitting in my debugger waiting on me. It's waiting for me to connect to it with the Chrome developer tools. So let me move this out of the way. I really hate these toolbars. All right, so I'm in the, right here, if I go to Chrome and you just type Chrome inspect, you'll see this is right here is my remote target. It's already found it, but if you don't find the port, you may have to set the port here. And then if I click inspect, you can see this is a debugger. I can step through code. I can set breakpoints to hold all of that stuff. So and here is my stack, the stack engine I discussed earlier. All right, so let me walk through this a little bit. All right, so here's that line where I check the application ID and see if it's equal to 0. Since it's already been deployed, it'll be 11 because that was the ID I got back. So since this is a BZ, it's not going to jump to label 1 down here. It's going to come through to this next line. All right, so this push bytes, this piece of line here, that is actually a method descriptor. I won't get into it, but it's a basically byte conversion of your method string. That's what that method opcode does. And then I'm going to look at my first argument that I'm being passed. And if I look at that, you'll see these two compare to these look the same. We'll do the equal and see. But I have two values on the stack. One is the method signature that I described, and then one is the one I'm putting in my, I'm getting from the calling app and just verifying that these two are the same. It'll pop both those values off the stack and push a 0 or 1. Well, since they're both equal, it pushes a 1, so I'm good. This assert will skip, since it doesn't have a 0 on top of the stack, but it will pop that value off the stack. So now my stack's empty. Okay, next thing I want to do is get those next two arguments, which happen to be the two numbers I want to add. So as I said, this is a byte array. You can see there's this long byte array. If I B to I that, this gives me the value 1. And I'm going to grab the second argument as well and do the same thing. And then I'm going to use the plus operator. I'll pop those two values and push a 2 on the top of the stack. So that's what it does. And then the last thing here, I'm going to store that. All right, now the stack's clear. If I were to return right now, the program would fail because I don't have a positive value left on the stack. So here's where I'm handling that whole return string stuff. There's that hashed return word. Now I'm going to load up my integer that I calculated, convert it to a byte array, and I'm going to concat those two together. And then using the log method, it'll automatically look for those bytes that are the return key And that's what it'll pass back to any ABI method that call any ABI compliant app that calls it. So I'm going to log that out. And then finally, I'm going to load a 1 on the top of the stack and then return. That's it. That's a successful execution of a smart contract on Algorand. All right, so now let's talk a little bit about PyTeal. PyTeal is a Python library that produces TEAL. This TEAL can then be compiled just like any other TEAL and put and deployed to the network. And you can compile the TEAL source just using the standard SDKs or a Go command line tool. But to compile to TEAL from Python, there's a special utility method in the PyTeal library that actually produces that. And I'll show that in an example in a second. But so if I'm looking at PyTeal, I have 2 programs that I have to represent in PyTeal. So we do these with what we call PyTeal expression trees. And I'm going to explain what each one of those are in the next slide, and you'll get an idea. But it's important to note that I have to create a PyTeal expression tree for my approval program. I also have to create one for my clear program. And by the way, almost all the applications I see, the clear programs just int one and return. I just let people exit out of an opted in smart contract if they want to. Most of the time, these 2 will be built in the same source file, Python source file. So before getting into what a PyTeal expression tree is, first thing we need to discuss is PyTeal expressions. And what is a PyTeal expression? Well, PyTeal expression is just a PyTeal object that compiles down to the equivalent TEAL. All right, and it allows you to describe different expressions in different ways that seem more that are easier to comprehend, and let it just go produce the TEAL for you. These expressions are created using PyTeal class methods. From the PyTeal library, we have a bunch of classes with methods that allow you to create these expressions. An expression tree is nothing more than just a collection of these connected expressions. So as a way of elaborating on that a little bit, let me just show you an example. All right, so here I have this simple line of Python. On the left side, I got a Python variable. On the right side, I got a PyTeal expression. Now that's just using the int PyTeal class to create a PyTeal expression. That's all it's doing. All right, so if I were to then use this utility method, compile TEAL, that comes with the PyTeal library, it's going to produce some TEAL. But before I do that, let me explain what this line is doing. The first parameter to this compile TEAL method is the expression you want to compile. That's generally going to be an expression tree. And then this mode. Mode can be either mode.application or mode.signature. As I stated earlier, we support smart contracts and smart signatures. TEAL is used for both of them, so you have to specifically state which one you're setting it for. And then version 5 would just be the version of TEAL that I want to produce. And then finally, I'm just printing that out. So if I compile that, this will produce that little bit of PyTeal, which you saw basically me walking through earlier, and it's quite simple, right? Now let's make it a little bit more complex. Let's say I have 2 expressions. You can see I got 2 Python variables and 2 expressions, int1 and int2. Well, you can use other expressions that take expressions as parameters. So in this particular case, I'm using an AND expression, and it ANDs 2 other expressions together. So in this particular case, this will produce, I don't know if you can see that. Let's see, that's a leaf. This would be considered a leaf expression. That's a leaf expression. You can think of that as the root expression. So that's my expression tree. I'm getting a little bit of feedback. Okay, I think it's okay.
Sorry, I think I just muted him. Yours should be fine now.
Okay, all right. So this AND is also an expression, right? So I'm just creating an expression tree with other expressions. This produces this TEAL, which is just loading these 2 values on the stack and ANDing them together, and then returning out from that. So that is the basis behind the way PyTeal is constructed up. Click back here. Every one of these expressions has to resolve to one of 4 data types. And the reason that for this is, as I stated earlier, the stack engine only supports integers and byte arrays. So that you can see that 0 and 1 in this list. Well, then we also have any type, which means I may have some expressions that return either a byte array or an integer. And then we finally have none, which means this operates on the stack, but it doesn't push anything to the stack. So it'll be nothing will be returned. And there are methods to do all of these. All right, so let's build this, start with a little bit more complex example of what an expression tree looks like. Let's say I want to create this logical condition in my smart contract. I want to look at my transaction amount and make sure it's greater than 10,000 and less than or equal to, greater than or equal to 10,000 and less than or equal to 20,000 micro algos. So the way I would do this is first I would create expression 1, which is my transaction amount. I would then create expression 2, which is my 10,000 micro algos. And then I would use the greater than or equal to expression, which takes 2 other expressions as parameters. And by the way, we also overload all the operators with the PyTeal library as well. So you can use greater than or equal to instead than the GE method. So that's the first side of the expression that I'm trying to create. Now I want to do the second one. So I repeat expression 1. Now I have expression 4, which that is the loading up the 20,000 onto the stack, right? And then I'm going to pipe those into the less than or equal to expression. So now I have expression 3 and 5 that are building up to the root of my tree. Well, now I can then create a new expression based on those 2 expressions. It's expression 6, and that's an and. So it's going to and those 2 conditions. So that's the genesis idea behind an expression tree. If I compile that TEAL, what that's going to mean, well, not TEAL, but if I wanted to write that in PyTeal, this is the syntax that you would actually use in Python. And you can see the and transaction amount greater than or equal to 10,000, comma, transaction amount less than or equal to 20,000. So that right there in the yellow, it is actual PyTeal code. Now, that may seem somewhat hardcore structured, but one thing's important to know is PyTeal has a complete set of flow control elements that allow portions or entire trees to be replaced or substituted based on conditions. For example, let's say I have this expression tree that I've built out as expression tree 1. And then okay, and let's say that I want that to be my the part of code that's executed on condition 1. I can also have expression tree 2 that I want to fire off on a different condition. So depending on some condition, I want one or the other to execute. This is flow control logic that you would do in PyTeal. Then this final expression would be a checking of those conditions and then returning the expression tree associated with that condition. The way you do this in PyTeal is using what we call a condition expression. And you can see here that we have two logical trees, tree 1 and tree 2 in our list. And a condition expression, all it does is take a comma separated list of expressions that has array elements that have 2 expressions. The first is my condition. The second is my expression tree. And then in this particular case, we have int1 equal int 0. You'll notice that entire thing is a PyTeal expression. So the condition has to be an expression and the body has to be an expression. So in this particular case, what the condition does is the first condition that's met true, it returns that body, that tree. So in this particular case, the first one's not going to be true. So it hit the second one and it would return tree 2. If we went through multiple conditions and none of them were, no condition was met, the smart contract would return a fail. So, and there's many flow control ones. We're going to talk about a few more later when we get into an example. All right, so speaking of which, let's talk about a PyTeal example. All right, let's say I have a smart contract, and we alluded to this one earlier. I have a smart contract that all I want it to do is increment or decrement a global counter. And the way I want to do this, I want to create an ABI method called add that takes one uint64 and returns a uint64. And what that should do when I call it is it should increment that counter. If I call it again, it should increment that counter again. That's the add method. Now, I also want to be able to subtract from it. So I need to be able to create an ABI method called sub that takes a uint64 and returns a uint64. And what it does is what it should do is subtract from that number and then return what that global counter is. That's what we want this simple example to do. Before doing that, I wanted to cover a little bit how you one of the primary things you're going to need to have access to is transaction property. So you use the TXN object in PyTeal. And here there's a method for every parameter that you can actually pull out of a transaction. The whole list is in the link below, so you can go look. And throughout these slides, you're going to see links to go get more information. But so I can get the sender, I can get the fee, the amount, those type of things. And you'll notice the type is the type, whether it's going to be a UN64 or bytes that's actually going to return and push onto the stack. So you get the idea of all the transaction properties. All right, I'm going to need that. But if I were submitting a group of transactions, I would have to use the GTNX array, which is just an array of TXN objects. So you can think the first transaction would be GTNX 0. And I can get the number that, so my code knows how many transactions were submitted at once. I can use a global variable called a method called group size. It just returns the number of transactions in the current application call. All right, so, but I'm going to use the TXN object for this and complete example. So the first thing I want to do, I told you early on that we have these 6 types of transactions. So first thing I want to do in every smart contract is handle routing which one of these types is being called to me. So what I'm going to use this condition expression we discussed earlier. First success breaks out of the condition. And then one thing that I did not state earlier is that every body element that you see in a condition has to return the same, evaluate to the same TEAL type. Okay, and that's if you can't mix and match those, otherwise your compile will fail. So if you look at, this is the first piece of logic I'm adding to my code. Now we are adding we're getting ready to release a bunch of PyTeal changes that simplify this a bit, but this is the way it works currently. We'll write an article and you can read about it when we get it. But this first line should look somewhat familiar to you. I'm looking at TXN and I'm calling application ID method. This returns the application ID. Well, as you recall, if it's being deployed, then its value is going to be 0. So then I'm going to use this Python variable to point at some other expression tree. So handle creation. So if the ID is equal to 0, I want to call off some expression that's called handle creation. We haven't created it yet. Then these are all the subtypes of application transactions I can have. This opt-in, close out, update, delete, no op. You'll notice I got this approve and reject in several places. An approval just means load a 1 on the stack and return. That's all it means. It's a shortcut for executing the smart contract. So what we're saying here is don't let anybody opt into the smart contract because we have reject. And so we have approve on all these others. Then we have the no op transaction. This is the primary one that people will use to call your smart contract. And you'll see I'm also linking off to a Python variable that should have an expression tree associated with handling no op. So first thing I'm going to do is handle the creation one. We'll talk about that. That's what I'm going to use to initialize my global counter to 0. In order to do this, I'm going to introduce a new flow control expression. That's called the sequence expression. What it does is it's a comma separated list of commands to run, and they're going to run one right after another. The only stipulation is that all but the last one must return be of TEAL type none, meaning you cannot do a sequence that loads multiple things onto the stack. So in this particular case, I'm using something called app.globalPut, which is our way of storing a key in global state. You'll notice I got bytes creator. That's the name of the key. And then I'm when you store a global state, it can only store byte arrays and UNs. Well, the transaction sender happens to be a byte array, and I'm storing that as the creator here. And then, so the next line then does int return 1. All right, and that particular one, you'll notice I only have 2 in that sequence, but only the last one actually pushes a value onto the stack. So, for example, a sequence of int 1 would not compile correctly. All right. So, and as I stated, app global put, I'm put 2 other examples here to show you what that looks like. We have storing a byte array, and then we're also having storing a uint64. So just using app global put. Okay. So in that handle creation logic you saw earlier, I'm going to chain this up into my Python code and put my sequence where I'm going to store this value called count, and I'm going to set its value to 0, approve the transaction in the run. So that's all. When you deploy it, that piece of logic will run. All right, some more details if you want to read about chaining expressions, things like that. All right, below. All right, so the next thing we need to do is I want to handle that no-op, but I'm going to need a couple things. First thing, I need the arguments array because I want to be able to switch on the ABI method, which one is being called. So we need the arguments array. As you recall, we have these 4 arrays that you can submit with every application transaction. Well, to access any of these arrays in PyTeal, you use a transaction object, and then you specify the array you're looking for. One thing that you need to be aware of is the accounts array in the 0th element will always contain the address of the sender of the transaction. The application 0 is a way of, like I said, calling other smart contracts. The 0th element will always be the current app. And then if you're using ABI compliant calls, argument 0 will always contain the method signature for the ABI call. Okay, I hope that makes sense. So this is all I need to go on to the next step. So I want to switch on the specific ABI method first, and then I want to call add or subtract depending on which one of those methods. So the way I'm going to do this is obviously I'm going to use application arg0 and I'm going to use application arg1. Arg0 will be my method signature. Arg1 will contain the actual value that I want to add or subtract. And then we're going to also use the equal operator because we're going to do a comparison. And PyTeal overloads all the operators. So the way I would handle my no-op logic expression would look something like this. First thing I'm doing is comparing the application arg0 to this method signature PyTeal function method that allows me to pass the method string and just compares the 2 of those. That converts to that same little bit of TEAL you saw earlier where I'm just comparing the method signature to what's passed in the 0th argument. And then what I'm going to return is this add function that I have not created yet. We'll create that next, but it's going to take application args1 and first convert it from a byte array to an integer, because remember, all arguments are passed as byte arrays. So I'm going to convert that to an integer, pass it to the function, let the function execute, and return what that function returns. Then we also have the same thing for the deduct, except the method signature is different. So that's all we do. Now, what I'm going to do next is I'm going to actually implement those add and deduct functions as subroutines in PyTeal. And these equate to subroutines in the TEAL that's actually generated. Some more links for you if you want to read more about either one of those. So to implement the add and deduct functions, first thing I'm going to look at is I'm going to need how I wrote that global counter, so I need to know how to go get it. So I'm going to use app.global get. What that does is you pass it the key name and it returns the value onto the top of the stack. And that can be a byte array or uint64. So in addition to that, when I'm doing subtracts, I don't want my counter to go below a 0. So I'm going to have to figure out some conditional way of not allowing that to happen. And I'm going to, in this particular case, I'm going to use a flow control if expression. And what it does is you put a test expression. If it's true, then it'll execute the body, the then expression, right? We also have the ability to do if then else's in PyTeal as well. So you can take a look at that. But from a standpoint of how we would actually implement this code, let's start with the add and see what it looks like. Now, don't get too worried about the return prefix. We kind of covered that already in the TEAL example, but this is just the way you create the return prefix in PyTeal. You can see the bytes and then literally the same bytes that you saw in TEAL. So we got this return prefix. You'll look down here. We also have this log method. That's the same log that you saw in TEAL. And here's my concat, and there's my return prefix. So this concat return prefix is this plus whatever I got in this. And what I have in this happens to be an app global get the current counter. And I add a bid. So I got to convert it back to a byte array. Both those concat, and then I approve it. But you'll notice when I pass the value X as a parameter, I first call app global get to get the current count, add X to it, and then I write that back in using app global put into the value count. So that's all that logic is doing. That's just a simple add. Now, where I need to use the if is on the deduct function. You'll see here, it's basically the same thing except I'm subtracting X, but I only do that if the current count is greater than or equal to X, because I don't want it to be negative. If you have a negative number and you try to push that onto the stack, your program execution will fail. So this is just a way of saying, okay, if it's going to make it negative, just skip it and log what the current value is and approve it in return. So that is the idea behind the add and deduct function. Is pretty straightforward. So if I want to compile this smart contract, first I'm going to show you the smart contract. This is, by the way, is going to be in the contracts folder. If you look here, I actually have two in here. This one's an example of raising X and Y, raising X to the Y power, if you want to take a look at that one. That was just there for a freebie. But this is the one I'm just wrote that you saw me do. All right, so here's where I'm importing the PyTeal library. And then here's the add function. There's my deduct function. And then I define a function called approval program that has all of the data that you saw me doing my handle creation, my method signature switch, and then the transaction routing. So that's all there. What you didn't see is, by the way, the clear state program is defined as approved. So just put int1 on the stack and return. Then I have these two getter functions, which these do is just go out and use the compile TEAL method to compile this expression tree, and that one compiles that expression tree for mode application, PyTeal version 6. And then once I actually want to write those out to disk so I can use them later. I actually could have just go directly called a Python SDK at this point. But here, if I just want to, I'm opening a file called app.teal and writing out the compiled version of that Python, that PyTeal program. And I'm doing that for both the clear and the approval programs. So if I want to compile that, first off, let me change directory into the contracts. In order to compile that, all I have to do is type in Python simple math.py. Oh, I must have typed something wrong. Yep, it's called a space. Okay, so it compiled, and you can see this is the TEAL that's actually produced for the approval program. And you can see this is the method signature check that you saw earlier. This is my add and my subtract. And it's got some other stuff. We won't go through that, but that's the TEAL that actually gets generated. And here's my clear program. This is just int1 return. This is probably going to be the most common clear program you'll see on the Algorand network. All right, so next thing I want to do is I want to run this. And the way I'm going to do that, first off, let me just give you a brief. I want to deploy and run this using Python. So let me just bring up my last bit of code here. All right, so this is actually the Python SDK for deploying or calling a smart contract. Think of this client in line 34 as just, I've already connected to an Algorand node and I want to issue a transaction. Well, the first thing I always do when you issue a transaction, get the network suggested parameters. That'll be like what the fee should be set to, what the current round is, the round range that you should submit the transaction, and that's what SP stands for. Well, the next thing you see in this is something called an atomic transaction composer object. And this is new for, we dropped this at the beginning of the year. What it allows you to do is build up a group of transactions very simply. That's all it does. But one of the things that supports is ABI. So it'll generate adequate ABI methods for you. So we create the atomic composer object, and then the signer is just, this is basically a way of pulling the key to sign the transactions. And in this case, we're just using a simple private key that we're passing an account transaction signer. All right, and then this method 1 and method 2. I told you earlier we store those in a JSON file. You can store those in a JSON file and use the SDK to read them directly up, or you can just instantiate them, an ABI method directly in the SDK like this. So here I'm doing add an array of arguments, which happens to be argument UN64, and what is returning. So I have add and subtract method 1 and 2. Then I use this thing, on the ATC, I can add any type of transaction in Algorand. But in this case, I'm just adding 2 methods and use the add method call. So first thing I specify is the smart contract ID I want to call, then the method I want to run, then the address of the whoever's sending it, then the signer, just the suggested parameters, then the signer, and then my actual values for my arguments. So what I'm telling the system, I want to call that method, add method with a value of 3, and I want to call the subtract method with a value of 1. So what this should do is my global counter when I first deploy will be 0, should go to 3, and then go drop down to 2 because we're subtracting 1. Then the nice thing about using the ATC is you can execute it and actually iterate over the ABI results that you define. So you can get your UNT 64 here. And that's the little bit of code at the lines 46 through 49 that you see. That's all that they do. So let me run that code and let you see what that looks like. All right. So here is in the Python directory, you'll see something called main.py. And this is, I'm not going to go through the whole definition of this, but this is essentially where we deploy the smart contract the first time. And then here is where this code I just explained where we talked about. And then finally, for your pleasure, I have a bunch of code commented here like this. It's basically for debugging. And there's two ways you can debug. You saw me debug with the TEAL debugger earlier, but you can also print out a stack trace that shows you how the AVM processes a program one line at a time. And so there's some code in here to show you how to do either one of those if you're interested. All right, so moving on, let me change to that directory. Then I'm going to run Python main.py. And you'll see it's going to show deploying the, oh, I didn't show it. I didn't print anything out on that. But you'll see this is processing my turn type. When I made that first call, it set my global variable to 3. Then when I called that second call, it returned a value of 2. So that's actually executing it from end to end. And all of that is in this particular example file. So that is a very high level view of the way PyTeal works and how TEAL works and how smart contracts work on Algorand. Let me give you a couple links that you'll want to have. Obviously, there's the link for the example code, and also the presentation is also in there. And then I want to make sure whatever you do, if you're going to develop on Algorand, join our Discord. We have a very active community there, and members of my team are on that. It seems like 24/7. So do that. And then everything that you saw today is documented on developer.algorand.org. Go take a look at it. We also have a forum if you want to post, if you prefer forums, and then Algorand's main GitHub account. And then Ryan Fox hosts our developer office hours, which is, we cover latest of things that are happening on the Algorand, in the Algorand ecosystem. You'll probably want to join that as a developer. So there's the link for that. And that's pretty much all that I have for today.
Awesome. Thanks so much, Jason. Big thanks to the Algorand team showing up, Ryan and Russell as well in the chat, helping out with all the questions. That is going to be it for today. All the information on the slides and a recording of this presentation will be on our Medium articles from Encode Club. So if you want to look back and look over what Jason was going over, you'll have those resources as well as everything we kind of posted here today. Thanks again, everyone. Thanks for showing up, and excited to see what you'll build through our hackathon on Algorand. And we do have another workshop coming up next week. Please look out for that. That'll be June 9th. So that's it. Have a great rest of your day. Have a good one. Thanks, everyone. Bye-bye.